Welcome to Circuit Insights. Today, we are going to understand one of the most important and most misunderstood components in electronics, the inductor. Most people memorize formulas and definitions, but in this video, we will understand what is actually happening physically inside the circuit. We will learn how current creates magnetic fields, how changing magnetic fields create voltage, why inductors oppose sudden current changes, why capacitors are not enough, and where inductors are used in real electronics. By the end of this video, you will not just remember the concept, you will actually understand it. Let's start with a simple straight wire. When current flows through a wire, electrons move through the conductor. Now many beginners think electrons move in circles inside the wire. That is not true. Electrons mostly move along the direction of the wire. But something interesting happens around the wire. A magnetic field forms around it in circular loops. So, electrons move straight, but the magnetic field forms around the wire in circles. This magnetic field is the foundation of how inductors work. To understand the direction of the magnetic field, we use something called the right-hand thumb rule. Point your right thumb in the direction of current flow. Now, curl your fingers around the wire. The direction of your curled fingers shows the direction of the magnetic field around the wire. This rule helps us visualize how magnetic fields form around conductors. Why we use a coil? A single straight wire creates only a weak magnetic field. But if we bend the wire into a coil, something important happens. The magnetic fields from each turn of the coil combine together. As more turns are added, the total magnetic field becomes much stronger. That is why coils are used in inductors, transformers, motors, and electromagnets. The coil shape helps concentrate and strengthen the magnetic field. Now let's connect a battery to the coil. At the beginning, current is zero and there is no magnetic field. As soon as the switch is turned on, the battery pushes electrons through the coil. Current starts increasing. And because current is increasing, the magnetic field around the coil also starts increasing. The important thing here is that the magnetic field is changing continuously while the current changes. And this changing magnetic field is the key idea behind inductors. Changing magnetic field creates voltage. This is the heart of electromagnetics. A changing magnetic field can create voltage. This phenomenon is called electromagnetic induction. A static magnetic field does nothing. Only a changing magnetic field matters. As the magnetic field changes, it creates an electric field around it. That electric field pushes electrons inside the wire. And when electrons move, current flows. So the real chain is, changing magnetic field creates electric field moves electrons, and moving electrons create current. This discovery became the foundation of generators, transformers, motors, and modern power electronics. Now we can finally understand how an inductor works. Suppose the battery tries to suddenly increase current through the coil. As current increases, the magnetic field around the coil also increases. And because the magnetic field is changing, it creates an induced voltage inside the same coil. But this induced voltage appears in the opposite direction. So the battery tries to increase current quickly, while the induced voltage tries to slow that change down. This is why current cannot instantly jump to a large value in an inductor. An important point: the inductor is not sending opposite current. Instead, it creates an opposite voltage that resists sudden current change. Now imagine current is already flowing through the coil. A strong magnetic field already exists around it. Suddenly the switch is opened and the battery is disconnected. But the magnetic field cannot disappear instantly. As the magnetic field collapses, it again creates voltage inside the coil. This time, the induced voltage tries to keep the current flowing in the same direction. This effect is called back EMF. If the induced voltage becomes very high, it can create sparks across the switch contacts. This is why inductors can generate dangerous voltage spikes when current is interrupted suddenly. Now, let's compare capacitors and inductors. A capacitor opposes sudden voltage changes. An inductor opposes sudden current changes. A capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. Both components store and release energy, but they react differently inside circuits. This difference is extremely important in filters, power supplies, and communication systems. How a capacitor works. A capacitor contains two conductive plates separated by an insulating material. When voltage is applied, electrons collect on one plate and leave the other plate. This creates an electric field between the plates. To suddenly change capacitor voltage, the amount of charge on the plates must change instantly. But moving charge takes time. That is why capacitor voltage changes gradually instead of instantly. Now here is a very important practical problem. In rectifier circuits, the capacitor does not charge continuously. It charges only when the source voltage becomes higher than the capacitor voltage. Because of this, charging happens only during short time intervals. During those short intervals, the capacitor draws very large current pulses. These are called current spikes. Current spikes can cause heating, electromagnetic noise, stress on components, and lower efficiency. Inductor smoothing. Current. This is where inductors become extremely useful. Inductors do not allow current to change suddenly. So instead of sharp current spikes, the inductor smooths the current flow. The current becomes gradual and continuous. This reduces noise, improves efficiency, and protects circuit components. That is why inductors are heavily used in SMPS circuits, chargers, power supplies, and DC converters. Real-life applications. Inductors are everywhere in modern electronics. Inside mobile chargers, inductors store and transfer energy efficiently. In transformers, changing magnetic fields transfer energy from one coil to another. In motors, magnetic fields create mechanical motion. In filters, inductors reduce unwanted noise and ripple. In radio circuits, inductors help select specific frequencies. Without inductors, modern electronics would not exist in the form we know today. Let's summarize the complete concept. Current changes inside the coil. That changes the magnetic field. The changing magnetic field creates induced voltage, and that induced voltage opposes the current change. So an inductor does not magically block current. Instead, changing magnetic fields generate voltage that resists sudden current changes. That is the true working principle of an inductor. Thanks for watching Circuit Insights. See you in the next video.